This is Chapter 10, Correlation and Regression. Section 10.1 is correlation. Correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. The kind of correlation that we will be discussing in this course is called linear correlation. This exists between two variables when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. Scatter plots show the type of relation that exists between two variables. There's 5 different scatter plots below. These are just all the different plotted points that you have between the two variables that are discussed in the problem. The first two are linear. They make approximately a straight line. The other 3 do not, and this is called nonlinear. This class does not talk about nonlinear correlation that we have between our variables. So right now we're going to be focusing on those 2 first ones that we have that are linear. The first scatter plot that we have has a positive relationship between those variables, and the second has a negative. From algebra, you guys will remember that positive slope has an upward rising and negative slope has a downward falling. We have positively associated and negatively associated. And positively associated is whenever the value of one variable increases, the value of the other variable increases. This is where it would have a positive slope, which is what we have right up above in the first graph. Negatively associated is whenever we have the value of one variable increases and the value of the other variable decreases. This is where we would have a negative slope, which is in that second scatter plot that we have up above. We have the next thing is a linear correlation coefficient. And again, remember, we're only dealing with linear models at this time. Is a measure of strength and direction of the linear relation between two quantitative variables. The Greek letter rho represents the population correlation coefficient, and r, lowercase r, represents the sample correlation coefficient. The sample linear correlation coefficient, r, is calculated by the formula that's given below. We will be using our calculator in order to find this. So get that next box a star. So find the correlation coefficient with the TI 83 and 84 calculator. In order to do this, we're going to go to stat. We're going to input in our data into L1 and L2 for those 2 variables that we have. Then we're going to go to stat to test into flin reg t-test. And we're going to be using this all throughout the notes for this chapter. And the way that this is set up is a little bit different than the other ones that we've had in our notes. So this is what you're going to have as your input screen. This is where you're going to be inputting in all your information. And this other box over here is going to be our output. This is what we would see after we hit enter on our linreg t-test. So on this, and this works for an 83 and an 84, for the linreg t-test, we're going to have our x variable into L1 and our y into L2. Frequency needs to be set to 1. For us, we're going to go ahead and have rho set not equal to 0. For right now, we have up above that rho is our correlation coefficient for the population, and we'll discuss this more when we get into the testing. The regression equation, again, we'll talk about later. And then we have calculate. So that's where we go down and hit enter. The output that we're going to have is a bunch of different information. And for right now, we are just looking at our correlation coefficient, which is R, which is the bottom one on here. And that value is going to be different depending on the problem that we have with those variables. So on the next page, it talks about properties of a linear correlation coefficient. So R is going to be somewhere between -1 and 1, and it could equal both of those. If R is equal to 1, then a perfect positive linear relation exists between the two variables. And you guys can see that on the last graph down here. And when R is equal to 1, those dots on that scatter plot are going to line up perfectly linear. They make a perfect straight line. This is very unrealistic for real life. If R is equal to -1, then a perfect negative linear relation exists between the two variables. The closer R is to 1, the stronger the positive linear relation is that we have. So if you look at that bottom row at our scatter plots, when R is equal to 0.5, we have our scatter plot is looking more like it's in the positive direction, but those points aren't too close to a straight line. However, if you look at when r is equal to 0.9, those points are getting more into a straight line, and then yes, when r is equal to 1, it's a perfect straight line. The closer r is equal to -1, the stronger the negative linear relation. And you can see that up above also with r equals -0.90. That is pretty close to a negative relationship that we'd have between those two variables versus -0.50, where they are still negative sloped. However, those points are not too close to a straight line, a little bit farther apart from one another. And then number 6 on our properties, it says the closer r is to 0, there is little or no evidence in the linear relationship between the variables. This could be a relation, just not a linear one, so not something we would cover in the class. And if you look at on our graphs up above, we have r is equal to 0, and it looks like stars in the sky. They do not look like they are approximated by a straight line at all. R is unitless, and R is very sensitive to outliers. So next it says, how do we know the correlation between two variables is strong enough to conclude that a linear relation exists? We calculate the critical value, and we're going to compare it to the correlation coefficient, and that is R that we have up above. So testing for a linear relation, we have two different ways to do this. The first one uses p-values, and the second is going to use table A6 to interpret R. So the first method is using p-values, and it says if the p-value is less than or equal to alpha, this supports the claim of a linear correlation. And if the p-value is greater than alpha, then this does not support the claim of a linear correlation. And we'll get more into this method later on. So for right now, we're going to focus on method 2, and this is using the table. So first thing says determine the absolute value of the correlation coefficient R. So remember, the absolute value turns that value that you have inside positive, so your value should always be positive. Second thing says to find the critical value. This is in table A6 in the textbook, or you can see the last page in the chapter 10 notes. And then the third thing says that if R, the absolute value of it, is greater than the critical value, then we say a linear relation exists between the two variables. Otherwise, no linear relation exists. So there's an example right below this that says listed below are the amounts of bills for dinner and the amounts of tips that they were left. Is there sufficient evidence that there is a linear correlation between the bill amount and the tip amount? So in order to do this, we need to use our calculator and get our correlation coefficient. And then we need to compare this to our critical value, which is found on the last page in these notes. On our calculator, we're going to go to Stat, to Edit, and enter in our values into L1 and L2. L1 are our X values, that's the bill amount that we have, and L2 is our Y values, which are dependent on the amount of the bill, which is going to be our tip amount. And we have a total of 6 different bills and their corresponding tip amounts that were left. Next thing that we're going to do is go to Stat and go over to Test. And we're going to go down to LinReg t-test. And again, we listed in our X values in L1, our Y values in L2. Frequency needs to be set to 1 because those are each an individual bill and tip amount. Rho is not equal to 0, and again, we'll talk about that later. Nothing needs to be in regression equation at the time, and for calculate, select enter. And for this, we are looking at our correlation coefficient, our linear correlation coefficient, which is our R value. So from the calculator, we get that R is equal to 0.828, rounding that 3 decimal places. And we need the absolute value of R. And the absolute value of R is still going to be positive, and it's going to be 0.828. And we need to also find our critical value, and I'm going to abbreviate that CV for critical value. And this is found on the last page in the chapter notes that we are looking at right now. So on the last page in the notes, or table A6, we have the critical values for our correlation coefficient R. And since we're dealing with a significance level for this problem of 0.05, we have 0.05 alpha. And the other thing that we have in here is n, and we need to know n, which is the number of values that we have. And so if you look back at your data, you'll notice that we have a total of 6 different bill amounts and also the tip amounts that correspond to those. So n for this problem is 6. And so since n is 6, we can read our table and get our value that we're going to be using from our critical value is going to be 0.811. So from the table, we get the value for our critical value is going to be 0.811. And our absolute value of R, which we have listed up above, is greater than our critical value. And our critical value, again, is 0.811. And this means, and looking right up above, if you have the absolute value of R is greater than your critical value, we say a linear relation exists. So we're going to go ahead and write down a linear relation exists. So it's asking for, is there sufficient evidence? And yes, there is sufficient evidence. So we have another example on the next page. And this one says the data below lists the ages of actresses and actors in the category of Best Actress and Actor, respectively. The ages are matched according to the year that the awards were presented. Is there sufficient evidence to conclude that there is a linear correlation between the ages of Best Actress and Best Actor? Should we expect that there would be a correlation? On your calculator, you're going to go to Stat, to Edit, and enter in your values into L1 and L2. L1 is going to be the actress's age, and L2 is going to be the actor's age, and both of those are in years. And then we're going to go to Stat, to Test, to LinReg t-test. Our X values are in L1, our Y values are in L2, frequency set to 1, row not equal to 0, and down to calculate. And again, at this time, we are using our R value, which is our linear correlation coefficient. So R is equal to negative 0.288. And the second thing that we are going to have to get is our critical value, which is on the table. So for this problem, we are going to assume that alpha is equal to 0.05. Again, if it doesn't tell us what the level of significance is, it's your opportunity to pick any value that you want, and I'm going to select 0.05 for this. And then we need to look at how many values we have for actresses and actors. And so for this problem, we have 12 total different actresses, and those match up with the 12 different actors. And our critical value for this problem is going to be 0.576. So from the table, our critical value is going to be equal to 0.576. And so we need to take the absolute value of R. And the absolute value of R this time is going to be positive 0.288. And we have to compare this to our critical value, which is equal to 0.576. And this time our absolute value of R is going to be less than. And from up above, if the absolute value of R is less than the critical value, this means that a linear relation does not exist. It says, should we expect that there would be a correlation? So for this problem, it's talking about different years of Best Actress and Best Actor. So let's just say that first year, we'll just make up a year, and I'm going to say this was in 2010. So in 2010, the Best Actress was 28. Should there be any relationship to the Best Actor's year? No, they have nothing to do with one another. So that would make sense why this value of R is close to 0, would mean that there's not a linear relationship that we would have between these two variables. But if you look back up here at the bill amount and tip amount example that we had, would this make sense that this is a closer value to 1? And yes, there is a relationship between the bill amount and the tip amount. Usually there's other factors that are going to contribute to how much you leave as a tip, but definitely the bill amount is one of those huge deciding factors of how much you should be leaving as a tip. The next thing that we have, it says the value of r squared is the proportion of variation in y that is explained by the linear relationship between x and y. So the example says, using the above example about bill amount and tip amount, find and interpret the r squared value. The value of r squared is actually calculated on your calculator, but another way to do this is take your r value, which for this problem was 0.828, and literally just square it. So if you were to square this on your calculator, we'll round 3 decimal places, we get 0.686. And so it says to find, which we did, and interpret. And again, remember, interpret means to discuss and talk about. So talking about this, what this means is that about, I'm going to rewrite that as a percent. This is 68.6% of the variation. In the tip amount can be explained by the linear relation between our two variables, which was bill amount and tip amount. We have a little reminder down here. It says, don't forget that correlation does not imply causation. We saw that back in chapter 1, along with a few other times throughout the semester. Common errors involving correlation. First one says, assuming that correlation implies causation. Lurking variables are one that affects the variable being studied, but is not included in the study. 2, using data based on averages. 3 is ignoring the possibility of a nonlinear relationship. If conducting a formal hypothesis test to determine whether there is a significant linear relationship between two variables, use the following null and alternative hypotheses, and use rho to represent the linear correlation coefficient of the populations. So for this, we're going to go ahead and give this a star. So if we're doing a formal hypothesis testing to see if something is a linear relationship between two variables, our null is going to be rho is equal to 0. This means that there is no correlation, and we're going to go ahead and squeeze in one little word in here. It is no linear correlation. And our alternative hypothesis is going to be that rho is not equal to 0, and this means that we do have a linear correlation. The test statistic can be found using, and I want you guys to notice we do have a t value there, a t test statistic, and the calculations can be done using that. It's also given to us on the calculator. There is another example on the next page that I want you guys to circle, and that is one that we will work out together in class.